So instead of using the Bohr model, we have an orbital diagram of the Schrodinger model. So notice that this is not a map of the atom where we're trying to draw it as it physically is. This is just a representation of all of our shells. You can see shells 1, 2, 3, and 4, and 5, and 6 are over here. Didn't have enough room to draw number 7. You can see all of our subshells, S's, P's, and D's, and F's. And the different orbitals are actually these lines. And these lines represent the shapes. Each line represents a different shape, which is really just like a three-dimensional graph given by an equation where an electron likes to be, where it exists and travels. Couple of features on this graph. Number one, the shells. The numbers represent how far away they are from the nucleus, just like the Bohr model. So this is a direct comparison. These 3D, that number 3 means these orbitals are in the third ring, the third shell. Except we don't call it a ring anymore, it's a shell, or an energy level. These 5p, that 5 is the important part, that is in the 5th layer of the atom. But notice they don't fill up layer by layer. 1, 2, 2, so far so good. 3, 3, okay. 4, 3. The D's happen to be a little bit out of order. They're a little bit higher energy, which is the next part of this. This is an energy axis. The electrons will go in the least energetic spot. Obviously, closer to the nucleus is better for the attraction to the protons, but sometimes especially in the smaller rings, there's too many electrons. The electrons repel them away a little bit, so it's actually more stable in a higher shell. So here we see the 4s electrons will fill up before 3d. Here, and that's for all of the D's are going to do that. We'll fill up 5s before we fill up 4d. You'll have some models of that as we go, but this is the order that the electrons would fill up. All we have to do then is, for any particular atom, figure out how many electrons we have, and we can map out its orbital diagram. Just count the electrons and start filling them up. Shorten that, please, with the electron configuration, which still gets a little tedious. Shorten that with a noble gas configuration. We could count the number of valence electrons, and we can actually give a valence electron configuration. And then if we have ions, we can actually start to make sense out of certain ions on why they are the way they are. So let's look first at magnesium. Magnesium has 12 electrons. So we start putting them in. And they go, electrons are going to come in pairs. We say one up and one can be down. There's a reason for that opposite. We call that a spin. 1, 2, 3, 4, 5, 6, 7. They spread out a little bit because they repel. And then 8, 9, 10, 11, 12. So this is what magnesium looks like. 12 electrons. The electron configuration then is just a shorthand of that. In the 1s orbital, we have 2 electrons, 2s2, 2p6, 3s2. We can shorten that again with a noble gas configuration. The noble gas says you go to the noble gas on the periodic table and you kind of say, okay, magnesium is going to be equivalent to neon and then 3s2. What that does is it kind of makes a break at the end of a shell. So the first shell is full, 2s and 2p, that second shell is full. So by saying neon, we say, okay, this is a noble gas here, a noble gas plus 3s2. So we can shorten them a little bit. How many valence electrons it has? Well, valence shell is the outermost shell. You can see it has, the third shell is my outermost shell. It has 2 electrons in there. The configuration, where are those 2? Well, they're in the 3s2 position. And then what charge does magnesium make? Well, we already know that magnesium is going to form a +2 ion, but now we can see why. This third shell has 2 electrons in it, kind of hanging out by themselves. If I take 2 electrons away, those 2 can come off really easy. we get a +2 charge. Notice here with the positive ion, we just lost the third shell. Ion configuration is going to be, for magnesium +2, 1s2, 2s2, 2p6. We lost a shell. This atom just got a lot smaller. A whole shell just left. It also tells us why magnesium is not +3. These electrons are closer to the nucleus. There's a tighter pull on them. It's Coulomb's law. These are farther away. I can pick off the far ones really easily. It's going to take a lot more energy to pull these out because there's a stronger attraction to the nucleus the closer they get to the nucleus. Okay, so this is the information we want to get out of the orbital diagram. This is the quantum mechanical model of the atom. If we did a different atom, let's do bromine, so we can get a little bit bigger here. Bromine has 35 electrons, so we can keep filling that up. Notice that all spread out, up, 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 down, 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 down. 1, 2, 3, 35 electrons. Okay, we can shorten that out. I'll just kind of continue on here. 3s2, 3p6, 4s2, 3d10. There's 10 electrons there, and then 4p5. The noble gas configuration. Okay, now it's down here in the third shell. This third shell is full after the 3p. That's where our noble gases stop. So we get an argon. It's going to be argon plus 4s2, 3d10, 4p5. How many valence electrons? Well, the highest energy level that's being filled up here is the fourth one. And that's here and here, but not there. 3 is not in the valence shell. 4s and 4p. That has 7 valence electrons. 4s2 and 4p5. To form an ion, I'm not going to remove them here because I'm really close to filling up that shell. I'm just going to add one more. Why can't bromine be -2? Well, it's really easy to add one because it'll be attracted to the nucleus. It's closer. But to get another one up there, it's going to be farther away and it's not held on very well. It comes off really easy, so there's not going to be enough energy given out to add a second one. But we can say 1s2, 2s2, 3d10, and then 4p6, and that fills up the shell for the bromine -1 ion. So this is a really useful model. Unfortunately, drawing Bohr models is much easier than this, but this is kind of what we're stuck with because we can't actually draw the quantum mechanical model. So this is just this is the information we want to glean from the quantum mechanical model. It's going to start to explain a lot of the size trends. Coulomb's law is at work all through here with the protons being attracted to the shells and how far away they are, as well as how many protons there are and versus how many shells and how many total electrons. We can see why the charges are the way they are. We're going to focus on these valence electrons, and we can actually get some ion information as well. So this is the quantum mechanical model of the atom.